Okay, so last week we essentially introduced the basics of the primary, we can call it, description of radiation that we will use throughout the course, what I call the macroscopic description. We introduced a basic fundamental quantity that we use in a lot of analysis of astrophysical images, spectra, those that you have seen, namely the specific intensity and the frequency integrated total intensity, as we call it, the monochromatic and the total. And then we also discussed how we can use this definition to define and discuss various physical quantities of the radiation field. We already talked about the radiation energy density. We introduced the radiative flux. And today, now, we're going to talk about a third important quantity in this, which is the radiation pressure, or in its general form, the radiation energy stress tensor. So, the first thing to realize, so to say, about radiation pressure is that it's actually fully analogous to gas pressure. It is, in that sense, the pressure of a photon gas. And as such, it is also useful here then to consider this little photon fluid picture when we set up a basic definition for our radiation pressure. So we can have a quantity here which will be our photon density. Now that photon density then is essentially just the number density of photons. So photons per unit volume. So that will then be the energy density of the radiation field divided by the energy of a photon. So h nu. Okay? And then we can just look at our definition, which we got last week for the radiation energy density in terms of the specific intensity, which was this one, and we can then just identify that the photon density here now is going to be then this divided by h nu, so just 1 over c I need either the C there or the C there, which you can also then just write as at this one, where then our I nu is just I nu divided by C h nu, and that's the photon density per frequency, per solid angle, or then, yeah, per steradian. Okay? So fairly straightforward. We will also use this then when we discuss equilibrium black body radiation, because we can just use them in order to get a feeling for the number of photons contained within a volume of black body radiation. Now here, though, we're interested in the pressure, which is technically the normal component of the radiation momentum flow. Okay, remember that we had this the first week. Photons carry a certain energy h nu, or if we prefer, hc divided by lambda, but they also have a momentum given by E divided by C. So apologize here now for the double notation in sense of the total energy density and the photon energy there. It's just standard, unfortunate. Hopefully it's always clear from the context. So this is just h nu divided by c. We should have skipped this. It would have been clearer. And that's then now the photon momentum, which of course goes in a certain direction, because it's a momentum. So you have a photon momentum h nu divided by c in some direction n hat, as we had before. And you have the photon flux, the photon number flux, which is a flux. However, now with the number density, instead of previously, we had the radiative flux, which is an energy flux. So now it's just this. So phi nu per, now again, unit solid angle and per frequency times c. So then this photon momentum flux, okay, you can look at how this is related to a pressure by considering the pressure as a force per unit area, okay? But that is, of course, then the momentum per unit time times area, okay? So then you can immediately realize, remember last week when we talked about the radiative flux as the energy per unit time per unit area. That was the radiative energy flux. That's why we can call the radiation pressure the radiative momentum flux in the same way. So again then we have to specify a direction which this goes. So you can have an area here, say, with some normal, and then you can have this momentum flux acting in a different direction, okay? So this would be the momentum flux in some n hat direction. It should not be parallel. And this is then the normal to the area, which is, of course, an imaginary area in space now. Of course, if they're in the same direction, then you have the direct normal component of the radiation momentum flux, but in more generality, you will have to decompose this in its 3 vector components and then split up there. And that is how you also build up stresses. And the analogy then with gas pressure is indeed the same. If we have static gas pressure, we actually have then an isotropic pressure tensor, in this case, with components only along the diagonal. However, if we have, for example, a liquid in motion, we can have shears. Yeah? Such shears then causes stresses in the same way as here, and that is then called viscosity. If you have ever seen, for example, a YouTube video on a viscous fluid, you will know what I mean. These are then the shear stresses. By analogy, we can actually then also have photon viscosity. Okay? Now, it turns out that for most situations, such photon viscosity, and one can realize this by dimensional analysis, for example, is normally not as important as standard viscosity. That being said, there are instances where you might have to take this into account. For example, in very luminous accretion disks around supermassive black holes, there are some discussions whether photon viscosity might play a role. Now, normally though, what is important is the difference in the different components along the diagonal of the radiation pressure tensor. And this is something that we will discuss further on now. So, from this, we can define our radiation pressure tensor here. We have this in now some direction Ni. The normal we put in Nj here. We could have just tilted it and put the surface in this direction. Then it would have been along another coordinate axis. We have to specify this is the important, and this is not necessarily in the same direction, such that the ijth component of the radiation pressure is this. And then we have the photon flux as h nu Ni Nj d nu d omega, whereby we can use that definition up here in order to realize how to put this in our basic quantity of the specific intensity. And we can also realize here that, okay, we can actually put this already now in so-called dyadic notation, like this. So this would be the radiation pressure tensor. I nu divided by C hat d nu d omega. Where, for example, if you put this on a Cartesian coordinate system, you will, of course, get pxx, pxy, pxc, pyx, pyy, pyc, pcx, pcy, pcc. So, to get a little better feeling for this, we will discuss a couple of examples next. We will do the same example as we did with the radiative flux. Yes, please. Sorry? We will come to actually now when this is the case and when this is not the case. When you have what I called photon viscosity, then the non-diagonal terms are non-zero, okay? And that happens in fully three-dimensional media. Like I said, typically those terms are small. They're smaller than the corresponding gas viscosity terms. Often. It doesn't always have to be like that, but in most situations. It is also always symmetric. So if you know, there are only 6 independent components at most. Okay? Now, just like when we discussed the flux, however, you will almost always have this referred to as the radiation pressure. Just like we talked about the radiative flux, which was then implicitly the flux in like the vertical or the radial direction most often. Even though we discussed to some length that technically flux is a vector with a direction, technically radiation pressure is a tensor. However, for most situations, we can identify the CC component in a Cartesian here, PCC, with just, we can call it P, and that is typically what we call the radiation pressure. Now, for completeness though, I introduced it generally, and we will also now just go into some cases where this is the case. Okay? So specifically, we're going to take the same illustrative example as we did for the radiative flux. Okay? For simplicity, we're going to work with the frequency integrated intensity. That's a notational thing. Yeah. So we're working with this quantity now. Okay? And then we're going to say that this quantity, which in general, as we have seen, is a function of 2 angles, theta and phi, but we're going to say that it's axisymmetric. That is only a function of theta. Go back to your class last week if you don't remember this from the radiative flux. That's how we could identify that in these situations, the flux in these directions indeed cancel each other. They were 0. We were left with only a net flux in that direction. So now we're going to see what this does with the radiation pressure tensor. Specifically, we're going to show that you can write it in Cartesian coordinates again in this form. E minus P divided by 2, E minus P divided by 2, and P, where indeed now I identified PCC with P, and as was pointed out from the audience, the off-diagonal terms are 0 in this case. So how did we now come to this conclusion? Okay, so I'm going to do 1 or 2 steps for you, and it will then be an exercise for you. It is included, the full solution in the exercise set, to complete this, okay? The way you can realize this is that, okay, we have this, and I've expressed it now as the p season component, but also the radiation energy density. Now, the radiation energy density, we know what definition it had. It had this, I divided by c, the omega. We have said that I is only a function of theta, not of phi. Okay, and then I'm just going to skip ahead the steps because we did all of these last week. So this is 2 pi divided by c minus 1 to 1 I of mu, where the mu. Okay, where again we remember that mu is cosine of our theta angle. Now, similarly, we can do the PC component as, then I'm going to write it out now, phi 0 to 2 pi, theta 0 to pi, okay? Then we have our I theta divided by c, and then we have to fill in for the radiation pressure tensor in the CC direction, NC, NC. Okay? And now we have to go back to our lecture notes again to identify what was NC. It was cosine of theta, remember? So therefore, in that direction, we have a cosine square theta. Okay? And then we had the solid angle, which is sine theta, d theta, d phi. Again, this is why I said that it's good if you get used to these type of integrals because they come back all the time. All right, so this is the p z component, and again we can see since this is only a function of theta now, we don't have any phi dependence, we can just take that out, so this is then just 2 pi divided by c, and now we have, I changed to the mu angle, plus I of mu squared d mu, okay? And following this, we just call this p. Okay. Yes. Okay, now let's look at the xx component. So, pxx is going to be then our phi to 2 pi, our theta goes to 0 to pi, okay? I of theta divided by c, and now I'm going to do the extra step here, nx, nx, xx component, sine theta, d theta, d phi. So then we're going to have to look in our lecture notes. What was this nx? That is the unit vector, x direction. It was sine theta cosine of phi, and then we have two of them, so squared. We have a sine theta d theta d phi. Okay, we can separate these integrals, right? Because again, I is only a function of theta. And this is where the complication, of course, comes in when I is not only a function of theta. Then you cannot separate the integral, so you cannot solve this integral independently. And that's indeed why you can also then end up with off-diagonal terms. Now here we can, so we're going to have phi 0 to 2 pi, and then we have cosine squared phi d phi, and then we have another integral here, which is a sine cubed. So that is then theta 0 to pi I of theta. I put the c down there. We have the sine cube d theta. Okay, so I make this note also about the integrals because I told you, like, for example, in, say, an exam situation, if you get an integral like sine theta or x, I expect you to know that. This is actually not a really trivial integral to solve. Yeah? So this I would actually give you some hint. How do you do this? Well, in this case, perhaps you might want to use the trigonometric identity that this is indeed equal to 1/2 1 minus cos 2 phi. Okay? So if we do this now, and we just save this, we call this integral y, then we can see that indeed this one here is going to be, well, it's 1/2 there, right? And this is going to come out as a sine, so I didn't even need to do the extra step, if I'm going to be honest, because we can do this in our heads. We know that the cosine becomes a sine, right? And we have 0 to 2 pi as an interval, so we should immediately realize that this is going to be 0 no matter what we do. So then we're just left with that, and that is 1/2, so that we can integrate. Yeah? So that's just going to be then 2 pi and a half, so we get out a pi. So in the end, we're just left with pi times this. And now we do our variable substitution, so we have pi divided by c, mu minus 1 to 1 I of mu, mu squared d mu. And now you should immediately realize, didn't you do an algebraic error there? Did I? I did. This is a sine. So it is this. Okay? If you see this, immediately shout out to me, okay? So, we have can split this integral then into 2, pi divided by c, the integral minus 1 to 1 I of mu d mu minus pi divided by c minus 1 to 1 I of mu, mu squared d mu. And hopefully now, and realizing this, you will see why I did that substitution. I'm going to try to keep this here now and stick to my one board. This one, you see that, okay, it looks quite a bit like this, the energy density. And here is where the angular moments come into play. Keep this in your head. Energy density is the 0th angular moment. So when you see this and there is nothing there, then it's like this is something like the energy density or the mean intensity, which is the straight one. Yeah. When you have a first moment here, then it's a flux-like quantity. It can be the Eddington flux, it can be the flux. And you see something like a squared here, a mu squared. Yeah. Then it's like a pressure-like quantity, or Eddington's K, a useful harmonic. So we had that the pxx component, indeed there we had pi, and here we identified this with e there. It's e divided by 2. As you can see, the second there is minus p divided by 2. And this is what we had there. Okay? So, your task in your exercise then will of course be to verify the PYY and also just take one of the off diagonal. Take one of them and just show that in the case that this is a function only of theta, they will be 0. If they're not, then I've done an error and you come back to me and tell me what I've done wrong. Okay? So that's the task here. Now we're going to look at this a little bit once we have done the mathematics of it and understood a little bit how we can connect the energy density, the scalar radiation pressure component, the PCC component, and look at some cases. Again, it's understood here that P is PCC. Okay. First, okay. Let's take the trace of this. You take the trace of your tensor. That's just summing up the diagonal. Then you can see that it's e minus 2 divided by 2 plus e minus p divided by 2 plus p. That's just e. So that's interesting. And that's actually generally valid. Not just for this case where we had I as only a function of theta. So no phi dependence. This, that the trace is always the energy density, that is generally true. And you can see this again by going back to the definition. Because these are unit vectors, which means that their scalar product is 1. If the scalar product is 1, we end up with this. This is the definition of the energy density. So this will be the case regardless of the dependence of the radiation field, even in a non-axisymmetric situation. Now, what you can also see is that in order to get an isotropic pressure, like we normally think of the gas pressure as being an isotropic pressure, to get an isotropic radiation pressure, there has to be a certain relation between the energy density and the pressure. Yes. Exactly. You have to have that 3p equals to E, where p again is Cc. Because if you plug in 3p here and there, yeah, then you get p diagonal. When this is not the case, then you don't get it. Okay? For example, if p equals to E, then you can see that, well, then we have the situation that it's 0, 0, and p equal to PCC, right? Now, we will come back to both of these cases, actually. This is the case for an isotropic radiation field. It is the case for equilibrium radiation described by black body radiation. Okay? This is the case for, say, the opposite direction, where we have a fully pointed source of radiation. For example, very far away from the star, you can say that the radiation field coming from the star then, and just going out in the space, has become radial. Remember, we sort of hinted toward that the last week already, that the angle subtended by, in this case, the star, well, if we look at the sun outside, it's kind of like this or something like that. But the further away I go, the solid angle that, or the angle the sun will subtend is going to be smaller and smaller and smaller until it appears as a point source. And then the radiation field is radially directed. We call it to be radially streaming. And then we can also show that in this case, P is actually E. So then we get this relation. This has actually consequences for example, when we when we use later on the moments equation, that is the energy and the momentum conservation equations of the radiation field, to derive also a wave equation, in order then to get the correct wave speed in the vacuum limit, which should be then the speed of light, yeah? We have to apply this. Whereas in this case, if we do this, which we will do as an exercise as well, we will get a wave speed, which is c divided by square root of 3. Now, nicely enough, we can actually identify that wave speed with the sound speed in the early universe. When the universe itself was completely radiation dominated, then the sound speed there can be derived by this, and it's in the limit that you can completely neglect the matter, it's indeed c divided by square root of 3. And to a first approximation, this is indeed what such sound waves are, what is imprinted on the cosmic background radiation that we see coming through us today, when it was first released at what is called the era of recombination. And if all of these terms are completely unfamiliar to you, that's fine. We will actually discuss them throughout the course when we come to that application. All right. We'll take a break there and then continue with the next part after that until 50. Thanks.